all I'm going to cover today is, well, review basically.
Yeah.
So exam 1, we do Thursday at 8. Our topics on it, all resistor circuits, all we've done. So we should have a series resistor circuit and be able to work it. Same current through everything, right?
Yeah.
Different voltages. Maybe rather than different, I'll just write voltages sum to 0. Right? My DC in for my source is equal to all my DCs out for my various resistors. Parallel. I have the same voltage on everything. Current sum. So the current out of the source splits and becomes the other 3 currents. I can write more on that if you need. Series parallel or parallel series. And that's as above for different parts of the circuit. All right, we worked through those in class, and I did videos of them. I left them up there. Is it worth me working through any of those now, or would you rather?
Not any of those ones, I don't think.
Okay.
I got those down pretty good.
Yeah. Now the next one is Kirchhoff's law is part of all of those. So the 2 laws there are, current into the junction equals current out. So all the current that flows into a connection flows out of the connection. And we can write a mathematical equation for it. In fact, we can actually frequently write a little summation symbol, all the current in equals all the current out.
Are we gonna get like a paper?
Yes, you get a full sheet. All my tests in here, you get a full sheet.
Okay.
So put anything in you want. You can put example problems if you want, I don't care. So that's the first one. The next one is voltage around a loop. Sums to 0. So if I did a sum of all the voltage drops or voltage rises as I go around a loop, that equals 0. So probably go in the direction of my battery, so I gain from my battery and I lose in each resistor. And that's true of every single loop inside a more involved circuit, and every junction inside a more involved circuit. Now we can use this to set up equations for those problems, like multiple sources. So I'll just write a couple down. I'm not going to solve them all unless you want me to. But if I have a circuit like that, here, I'll just put a resistor here. I can solve that one pretty easily by 2 methods, actually. Number 1, I can go in and do these 3 resistors are in series, right? Replace them with a single one.
Yeah.
That resistor's in parallel with this. Combine them, replace it with a single resistor. That resistor then will be in series with these 2, and I end up with just a series circuit. And I can go where I'd write all of them out, so I would come through and each step I would write them out. So combine those 3. Combine these 2. I'm left with a series circuit which I can solve. Find that current. Find these voltages. If I go up here, I'll call this V1, 2, and 3. Go up here. This current through this resistor, through here and through here, that's the same current as I found there. Let's call that 1. The current through this resistor is going to be the split of these two. So I'll end up with the current down here. These two voltages are the same, they're both V2. Go back up here, and this current, I guess I could also write my V1. V3, yeah, 3. So those stay the same. I2 stays the same. This is still V2. Over here I have I3, and I end up with, whatever I'm going to call it, V4, V5, V6. Just use an Ohm's law up and down, series of parallel resistors. Now if I wanted to, I could use the Kirchhoff's laws and set up a series of 3 equations and solve for them. It's probably a little more algebra, a little less graphics. I think most people find it more difficult, but I can do it. I have to do it if I have a problem like this. There's no way to reduce that. So my only choice, if I have one of these, is to come in and say, okay, here's a loop. I'm going to go around this. This is not my current now. I'm just calling this a loop. I'm going to go this way. So if I go up here, here's my junction. That's 1 and 2, but they're going to be the same. So if I go to the junction, I'll make this I1, this I2, this I3. Doesn't matter what I label them as long as I keep it straight. I1 and I3 flow in, I2 flows out, so I2 equals I1 plus I3. Then I would go around loop 1, right here. I'd probably start on the side of the battery. And I'd put, the battery voltage in, subtract current 1 through this resistor, called R1, R2, I don't know why I made that a 5, R3, so current, voltage drop, that's all be 0. So I go around that loop, the voltage I can get brought in from the battery, subtract all those other ones. And then I would come over here on this one and do the same thing. I'll start right there at loop 2. Go up. So that's my second battery. Subtract current 3 through, let's see, R3, cut off R4 and R5. Subtract this. Yes, that is the same voltage drop as here because you're doing the same. Subtract this, which is I3 R5. Now, presumably, if I have all the resistances and the battery voltage, I can plug those numbers in now. Drop all my units. I have my 3 equations, 3 unknowns. I'm going to have to do some algebra, some substitution, and solve that. There will be a problem that makes you do the Kirchhoff's laws problem equation. So make sure you can work through it, review the homework on it, we did a lab with it even. It's not last week's, I think.
Yeah, so.
Okay, so.
Or it was the week before last week.
I mean, when you get down to it, what have we covered this semester? Series, parallel, Kirchhoff's laws, and then the other big one's voltage dividers.
Yeah.
So I'll write that down here, voltage dividers. In the end, a voltage divider is just a series circuit. We're looking at the voltage on one end. So the voltage across any given resistor is the battery voltage, or the source voltage coming into it, times that resistor over the total resistance of everything in series. So we have a couple problems we're going to work with this. One is, actually, there's several, I guess. Is we just have 2 resistors. The voltage here is just straightforward. Battery times R2 over R1 plus R2. So should be able to handle that. Now, the ones that are I would be more likely to put on are probably something like we did in lab with the potentiometers. Said, hey, here's a resistor 1, here's a resistor 2, here's a potentiometer. Find this voltage based on where the potentiometer is set. So if you do those, just treat this as a resistor, find the current, find these voltages. The potentiometer is all the way down here. The reading will be that voltage. If it's all the way up here, it'll be those 2 voltages added together. If it's some fraction in between, it'll be the fraction of the voltage on that part of the resistor plus this. All fine?
Yeah, I think so.
Now, the next one is, well, this is great. I got a resistor. I got another resistor. Over here, I have a load. My load needs 15 milliamps and 5 volts to run. So I've got a 12-volt source. Pick my resistors. Any resistors I want.
5 kilo.
Yeah. So here's what I'm going to do. I'm not going to pick resistors first. I'm going to come over and say, I need 15 milliamps to run over here, right? 15 milliamps. I'm going to just pick 1 milliamp. That's kind of a standard thing to pick for this. I need some current going through it to create a voltage. So let's pick a small current, at least relative to that other one. So if I do that, R2 is going to be 5 volts, because it's parallel with that, over 1 milliamp. So yeah, that's exactly what you picked. I think that's look at the draw though, isn't it?
Yeah.
And then I'll double check power real quick. Now I don't have a problem here because 1 milliamp times 5 volts is 5 milliwatts. So there's a good chance I'll tell you to pick it. You can just pick a quarter watt. You can use an 1/8 watt. It'll be fine. Now R1. It's going to be 4 volts over 16 milliamps. So I have 4. That's 250 ohms, right?
Yeah.
I double check. This can still be a quarter watt. Watch out. A lot of times for these settings, this one you might get done and you calculate power and realize it's got to be like a 1/2 watt resistor or a 1 watt resistor because the amount of current flowing through it.
Yeah.
All right, so something like that with the load. So we did those homework problems with like the switches you open and close to set, they do different loading and shift the voltages. So you should be able to handle that, or maybe I put a resistor over here, then you go, okay, the parallel combination of those resistors, the actual drop in current. Okay, that's what things we're going to have on there. It's going to conclude what we did the first part of the semester, which is, I mean, these are largely review from the first semester, just expanding them more to typically 3 or more resistors. This wasn't really review because we hadn't covered last semester, but it's a straightforward expansion. This should be too, but I think most people find this math a little difficult. Not that they find, the concept isn't so bad, but getting through the algebra can be kind of painful.
Yep.
And voltage dividers, I don't know if the algebra is bad there. It's just kind of remember everything that's going on. Like, oh, my loading then changes all my voltages and currents, which changes, so it's just keeping track of everything that's going on. We'll get this week done. This week's lab is out there. Homework is out there. Homework's all review. Next week, we'll start into what we call the networking theorems, which might sound like I said, like networking, but it, but it doesn't. It has to do with how can I handle problems where we set up these Kirchhoff's law equations. They will solve those problems, but we can do bigger problems. We can either do these same problems with a little less mathematical work, or bigger problems with maybe the same amount of work. And so that's what most of the rest of the semester will be exploring, those networking theorems. We don't have to worry about it next week. Any questions?
How about like what we've had on the assignments, like past 1 or 2 weeks, like battery questions and like polarity and stuff. Like, will that be on here?
I probably, well, yeah, I could do. You mean like polarity of measuring voltages and stuff like that?
Yeah, and then we've had like stuff where we gotta measure the different wire resistance and those kinds of things also.
It could be. This is the main thing I want to do there, but I would have that resistor equation, or that resistance equation on your sheet, but I will give you the tables with the numbers if you need them.
Okay.
Just like you should have the color codes available to you, because I might ask you a problem that requires you to like go, okay, let's interpret this resistance. I might ask a question that says, here's this circuit you see on the board, find all the, draw the schematic and write all the voltages and currents.
Mm-hmm.
I have those kind of, I could have those ones that interact more with the lab into stuff.
Yeah. All right.
Definitely, yes, it's possible. But if I do ask you anything on resistance or resistivity, I'll give you the numbers, because I don't want you to need to bring all that entire table into the
Yeah,
text.
that's just what I was curious about.
Yep. Otherwise, I'm gonna let you get started. Do lab stuff.